All right, it's the top of the hour, and we're gonna wait another minute or two as people will continue to arrive. But welcome everyone. My name is Diana Sinton. In today's iGuide virtual consulting office, we're going to hear from um, Jinchi Ye uh, from University of Illinois Urbana-Champaign. She's part of the iGuide community. She's a graduate student at UIUC, and we're excited to be able to hear about her work. As I said before, this session will be recorded, and if you go to the iGuide website, we can see. I can't do it right now, but I will make sure that we put the session into the link into the chat for where all of our iGuide forum recorded VCOs, I'm sorry, are recorded, and you can access those links. This is a regular Zoom meeting, so we appreciate you keeping your own microphones muted during the presentation. There will be time for question and answer following the event. And let's see, Tinchi, I'm going to stop sharing mine so that you can now share yours.
All right. Thank you, Diana. Yeah.
And with that, yep, the rest of the participants will continue to sign on, but let's turn it over and get started. Thanks very much for presenting today.
All right. Thank you, Diana. Yeah. Hello, everyone. My name is Dingqi Ye from CyberGIS Center, University of Illinois Urbana-Champaign. And today I'd like to introduce rs-embed, which is a tool designed to make remote sensing foundation model much easier to use in practice. As we know that foundation model are clearly changing the remote sensing. Unlike a traditional model designed for a single task, this kind of foundation model are pre-trained on large-scale Earth observation data and learn more general transformable representations. So in practice, what we often want from them is a embedding, which is a compact numerical representation of the region. The same embedding can support many downstream tasks, from environmental monitoring to agriculture to urban analysis. But there is still a gap between the promise in theory and usability in practice. So when we want to use remote sensing foundation model, we usually do not begin with a clear tensor ready for inference. We actually more likely to begin with a real question. Like for example, how is corn growing in Illinois this summer? But between that question and the final embedding, there are many painful steps. Like we need to acquire imagery, reconcile the model-specific input requirements, handle the different spectral and image size, and sometimes incorporate additional inputs such as a wavelength, time, or location. So on top of that, each model typically comes with its own interface and the pre-processing assumptions. So as the result, a lot of research time is spent not on the actual scientific question, but on the glue code. So that is really the starting point of our rs-embed. And the motivation behind rs-embed is straightforward. And that is, can we reduce the whole process to something much more natural or much more standardized? So rs-embed lets users think first about their scientific question, like when, where, and what kind of output they need, instead of forcing the user think first about the model-specific pre-processing pipeline. Then the tool will handle the rest. At the high level, the workflow is also very straightforward. Based on that, rs-embed automatically fetching the corresponding imagery, performs the pre-processing required by the select model, run the inference, and then return a standardized embedding output together with the metadata. So rather than manually stitching together the data acquisition, formatting, inference, and exports, the user can focus on the region and the time of interest, while rs-embed can handle the rest. And that brings us the three things that user actually needs to define. So one is where, of course, like user can define the region of interest, for example, with a bounding box or a point of buffer. Another is when. So people can specify either a year or time range for their interest. And also the shape. So people can choose the form of output such as pooled embedding or grid embeddings. So an important feature of rs-embed is how it handled the temporal observations. Because in remote sensing, time is often not optional, right? Many phenomena are seasonal or dynamic, and a single image may not be enough. So, but to dealing with that kind of situation, different model also treat time differently. Like some of them just accept single input images, while another are designed for the like temporal dynamic and can directly take time series input. But for both cases, RS is supported them both. Like for the single input image models, it can fuse the images across a time range using strategies such as the median or mosaic. For a temporal model, it can directly pass a sequence of observation to the model, then get the embedding. And the different model also expect different input resolution and shapes. So this is another place where user often ended up writing their custom code or using the foundation models. So to address this, rs-embed also supports a flexible input preparation strategies. So one option is to resize the region of interest so to fit the model expect input shape. That is a really straightforward and a really fast way to dealing with that kind of stuff. And another option is to tie the region into a finer, high-resolution native grid to preserve more detail. So user can choose between the convenience and fine-grained depends on the needs of their downstream task. And not every task needs the same kind of embedding output. Like sometimes we only need a single vector to represent the entire region of interest. That is useful for tasks like classification, retrieval, or similarities research search. But in another case, we might want a spatial structured embedding field represent as a 3D stack of grids because we care more about the internal spatial variation or pixel-wise analysis. So rs-embed also supports both pooled output and grid output, which make it easier to connect embedding to a wide range of downstream tasks. And another design goal of rs-embed is to scale smoothly from small experiments to large studies. At the smallest scale, user may want one region with one models. At the medium scale, they may want many regions with one models. And at the large scale, they may want a region across the many models. So with a batch export for downstream analysis. So the workflow involves from interactive exploration to large-scale embedding exports while keeping the interface consistent. So of course, we have also optimized the efficiency in terms of large-scale acquisitions. By leveraging the thread of and the GPU parallelism, we have minimized the waiting time for users such as much as possible. And currently, nearly 20 mainstream foundation models are supported in the rs-embed, and some of them are on-the-fly model, while others use pre-compute embeddings, and some of them are designed for time series settings. The key point here is not just the number of model, it is that user can access them through a more unified interface that reduce the friction and make cross-modal experimentations much more practical. To show how rs-embed work in practice, we also create a demo using that. So we actually use 991 distinct sample point data from summer of 2019 and random forest model for the downstream task. During this whole process, we obtained the embedding of 10 foundation model in that region and time by merely using the export batch function once. So user can return to subsequent model design and their own research without worrying about the troublesome process. So if you want to do the things by yourself, that will be really a disaster because actually you will do the like collecting data, pre-processing, run model output 10 times. It's really time consuming. But with rs-embed, you can just use the export batch this function and call this once and to get them all. Right. So yes, we also do some visualization of this kind for some of the foundation model embedding. The strategy for visualize here is we use PCA to select the 3 main channel and to do the pseudo color display. And here is the 40 models embedding for the same region and time. So for the visualization, you might have like quick impression of which model their characteristic and their features, so you can choose them, which one you want to use. All right, so I introduce a lot. So here I want to share you guys with some quick example and the important link you might interest. And the first is the GitHub link of rs-embed. Right. So in this link, you can see the overview of rs-embed and all the code here, and it shows like how you install them. It's really easy. You just do the pipe installs, and everything is settled down. And if you're the first time using that, you might need to do the authenticate for using the Google Earth engine. And all right, there is some quick example and visualization in main API and the model list here. And all the demo and the function that I mentioned before is that you can all find the code here in this repo. Right. And another link I want to share is yes, I want to show you guys with the quick like the playground of rs-embed in iGuide platform. So sometimes you have to set your own environment to run the specific package, right? But in iGuide platform, we have everything settled down, so you can just search the rs-embed in this platform. Right, and you can just run the node, click the run notebook here. And you will see the rs-embed playground notebook. And for default setting, you can choose the kernel here. There is a kernel list. You can choose the rs-embed, and everything is settled down in here. So, right. So I want to show you guys how rs-embed used in practice. So before that, you might need to pipe install the rs-embed. Yeah, but for the kernel, it's already contain everything, so it's already satisfied. Right. And after that, if you're the first time user, you might need to do the authorize for Google Earth Engine, because for the backends, we fetch the satellite images from the Google Earth engines. So you might need to do this once, but it's only once. You don't need to like authorize it every time. So I will authenticate it just to show you. All right, there is a link. So all you need is just to click the link here and you will see this page. this is my Google account, and if you use Google Earth before, Google Earth Engine before, you can choose the project you already have. But if you don't, that's also okay, because you can easily click the create new cloud project here, and just select, and it might take you 3 to 5 minutes to finish a questionnaire, and you will have the access for the Google Earth Engine, and then you should back to the yeah, and you can back to these pages and select existing the cloud project, and for me is this default project, and you just click the select, and all you need to do here is to generate the token. Right. Let's change it to English. Right, and click the continue, everything continue. Right, you got the code here. So you copy the code and back to your notebook and enter the token here. Right, so it's all set. So next time you don't need to you run this, it will not force you to re-authenticate it again. So it's quite simple, right? Like just like this. After that, you can just run the rs-embed. And here is some tool function that I will use for display. And yeah, let's start for the rs-embed part. Firstly, is to define the space and the time you want. We have actually two simple ways to define the place you want. As I mentioned before, one is to create a point buffer. That means you tell the function the center of your place and how large is your buffer, and that will create a rectangle for you to represent your space. And another thing is you can use the bounding box, and then so you might need to tell the function the minimum latitude and minimum longitude and maximum longitude and maximum latitudes, and to create such kind of bounding box to represent your ROI. And another thing is the time. It's also quite simple. One is you can directly tell the function which year you want. It's just like after you tell them like and the year, the time. So and another thing is the you can define the time range like this. For here is I actually define a range like the 2022 summer, right? So it's really flexible, and for each you can choose whatever you want, depends on your demands, your downstream tasks. All right. So next things we want to do before we get embedding is you might want to have like a quick look for the place you defined. So we have inspect provider patch function here. You just tell the place, tell them the time, and the sensor you want. It's basically like the Google Earth Engine. It's collection and band. We can run that, and they will return the imageries directly from the function, and you can see all right, our region of interest is like this. So after check everything is okay, then we might want to get the embedding directly. So for the minimum usage of rs-embed is you have a region of interest for one models. So what you need to do is just tell tell the function, use the get embedding function and tell them which model you want, which place you want, and which time you want. Right. And so this quick example use the alpha Earth embedding, which also is for the model is Google Satellite engine. So it might take you a few seconds to get the embedding right. So for that regions, we directly get the Google of Alpha Earth embedding like this. That is the minimum usage of this API. But and another feature that I mentioned is we can choose the pre-processing for the input image. One is to resize that, one is to tile that. So to use this to adjust this parameter, you need to name the input prep this hyperparameter at like this. So let's try this. So here we use the swirl foundation model for the same place in the same time. Right. All right. So the results pop up. So if you can see that if you choose the resize, the grid will be more sparse and the spatial resolution is lower. But if you choose the tile mode, it will protect more spatial resolutions, more detail of the regions. But it's actually a trade-off. For the default setting, we choose the resize because if you choose the tile, it means it has like a multiple times computation rather than just do the resize. For the resize, you only need to reference once, but for the tile, especially for the large regions, it might do like 9 times or even more times of inference. So you need to wait for a long time. So this is the strategies. It depends on how many computer source you have. If you just have like me using the CPU right now, it may take you more time when you choose the tile mode. And another feature we have is we can choose which output form we like. Like as I mentioned, if you just want to do the classification or like retrieval, this kind of task, you might just need you only need is one-dimensional pooled vector, right? But for if you want to do more like pixel-wise task, you might need the grid output to protect more detail of the regions. So we support them both. All you need to do is to use these parameters, output, and select which mode you want. Right, it's really quick here. So so for the pool, you can see that it's just one-dimensional vectors, but for the grid shape, it's a 3D stack tensor. And to scale up, sometimes we don't have one single region of interest, right? So you might want many region of interest for one model, and you want to get them as a batch. So we also provide the API. It's basically the same as the get embeddings API. So but the only difference is in the previous, we only tell the function one single point, one single regions. But here I create a list that contain all the region of interest that I want, and the rest of them is basically the same. So the API will also return a list of the embeddings. So we will show here. Right, we get 3 embeddings, and each of them is 1024 channels, and with 40 height and width. And the last API we have is the many ROI times the many model. It's the most complicated, or I would say most playable API we have. It can be really customized, depends on your demands. It basically it contains all the function, all the information you want from rs-embed. So not only it supports the list regions, but also it supports a list of models. And for example, you might want like remote clip, pre-survey, and Terra FM, this kind of model. You can just tell them which model you want. But sometimes we even need like more detailed setting of the specific model. For example, for the Terra FM, for the default setting is they're using the Sentinel-2 imagery as input. But sometimes you might want, okay, I want Sentinel-1. So you can use the export model request, this kind of function, and to adjust the model specific configuration. So here I switch them to the Sentinel-1. And right, you also can tell the function which type of output you want. And also you can also save the input images by set the save input parameter here. And also the input prep ways. All right, so after running the function like this, you will get a file like exports. We can see that we have 2 points, and so they have two JSON file and 2 MPZ file. The JSON file is it contained all the metadata it have, like the projection, the buffer, the spatial information, and the temporal information, like this in summary. And for the MPZ file, it contains the embeddings, and as well as the saved input. Let's check what's here. Right, so if you just use the inspect export MPZ like this, and you can see, right, the metadata we have, and the input data we used for get the embedding. For the remote clip is actually RGB 3-channel foundation model embedding, foundation model. So it's just a 3-channel for these regions. But for the Terra FM, as I said, we set it to Sentinel-2. So the input images is 2-channel. One is VV and one is VH. And we also do the visualization for these 2 embeddings. It's like this. So that's basically all the API we have in rs-embed. And yes, for more information, yeah, back to this, I highly recommend you to use the documentation we have. Is this link. Right, you can also find it in our GitHub repo. You can just click the doc here, and you will see all the documentation we have. And before they have like quick introduction, like quick start, tell you how to install, and all the example that I have in the notebook. And one thing I want to emphasize is I highly recommend you to learn a little bit about the settings before you start your large-scale investigations, because for the rs-embed, some default settings are chosen to balance the computational cost. Like as mentioned, we choose resize as default settings rather than tail, even though tail can contain more detail of the spatial information. But so if you want to have like best possible settings, so you can refer to this documentation, and so you can figure out which is the best for your platform, which is best for your computation resource. So all the information is here. Like also we like some support the model variant. Some of the foundation model provide like tiny, small base and large this different type of model. So you can also you can also access them by tell the function the hyperparameter. And another thing is the models. We have the documentation here. Every model we have its own pages. Like we have a quick start in the 30 seconds. Like what is the model? What is the how it's trained? What's the feature of that? And also we have the pre-processing pipeline and architecture. Like you might know how we get the embedding with rs-embed. And some of them have like environmental variables. So if you want to investigating more, you can set the environmental variable like this. And also we provide some example like for like we can switch the modality Sentinel-2 and Sentinel-1 is totally up to you, your demand. And right. For the soil, you can also set the patch size, which can help you to gain more higher quality embeddings. And also we have the API documentation for sure, the signature, the metadata, and when to use them, and the rule, everything you need you can find in these API pages. Also the inspect. Yes, and for rs-embed, we also have the extending pages. So if you are currently developing the remote sensing foundation model, it's welcome for you to use rs-embed to extend your work, or use rs-embed to compare your work with another as a benchmark. So it's also really easy to do that because we actually have a good interface. So all you need is basically to right. So all you need is basically to register in the core, and then you have your own embedder file on the embedder. So it's it's really easy to do that. And we also have a contributing guides, so you can maybe further push your give us PR to rs-embed, so you can have more people to easily access your work. Yes, that's basically all for the quick example. Let me know if you have any question. So here's the conclusions. To summarize, the main contribution of rs-embed is not just another model wrapper. It's a attempt to simplify and standardize the entire workflow around the remote sensing embeddings. So the core idea is let user describe the problem in natural term, like place, time, and design output, and then automate the difficult part like data fetching, pre-processing, inference, and scaling. By doing that, we hope that to lower the practical barrier for using RS foundation model and to make ecosystem more open, collaborative, and accessible. So this research was primarily supported by iGuide and also benefit from TGI Rail systems. We would also like to thank the following organization and projects that make rs-embed possible: and Google Earth Engine, TouchGeo, TerraTouch, and GeoTessera RSHF. And this library is also built upon the incredible work of our remote sensing and geography community. And actually, we get a lot of feedback from the foundation model author. We really appreciate that. So that's basically all. Thank you guys for listening. Yeah.
Thank you very much, Jinky. I'm sorry, I stumbled over your name.
Yeah.
Are there any questions from the audience right now?
Maybe one.
Sure, Stuart.
Hey, let's see. When making a request So, uh, I'm sorry, I missed part of your presentation, but I saw you were giving advice as to um, how to limit the scope to not ask for more than you need. And I'm wondering, before you make a request for what might be a large amount of data, does the system give you an idea of gauging how much you're going to be asking for?
Oh, you mean the uh
So for example, you might ask for something that has some time span, and you're not really sure how many satellite images over that time span, over that area, how many of them might exist. So you might think of it as being if there are three satellite images over that time, well, that's one thing. But if there are 500 of them, you might say, oh, I really want to choose a sparser time sampling, or that sort of question. Do you know before you've set the whole machinery in motion, how much it's going to, how much of a burden it's going to be on the system to ask
uh
for it?
I see. Currently we will not tell the user directly, tell them how much they will, how many imagery they will use. But that was a good suggestion to let people for further development for the system, uh, to let user to better understand their request, how large is the request. Yes, but we actually write all the information in the metadata, so you can find them after you get the the embedding, but not before you get the embedding. So, yeah, that's a good suggestion actually. Yeah, thank you.
Okay, thank
Yeah.
you.
Thanks for that question, Stuart. Anything else from the audience right now?
I have a question.
Yes, Ethan.
Hopefully you can hear me all right.
Yes.
Hi, Dingji. Really impressive work. Um, I was wondering, is maybe you mentioned it, is the data normalized, the embeddings when you get it back? What is the data range?
Uh, what?
Like the
Sorry.
scale, the per pixel scale, data scale? Is it 0 to 1, 0 to 255?
I see. It's actually all right. That's a really good question because different model has a different assumption for their input data. So it's highly depends on which model you choose. For example, if you want to let's see, let's say Preserve. So I remember. So some of them actually the range is really different. But for when we developed our rs-embed, we actually refer to their own code repo and to see how they standardize, how they're dealing with that kind of data range. But some because like Sentinel-1 for some Sentinel-1 the data range is really high. So for how we do the pre-processing is actually follows the author how their own author do. So it's highly depends, but it's not standardized for all models. Yes, I don't know if that answer your question, but I think
Yeah,
we actually customize for each model, and
that
they
makes sense.
yeah, because they have a different assumption when they're doing the training. We cannot say we have a one single like gold normalization strategy to suit
Right.
them all. That don't make sense, right? So yeah.
Yeah, that makes sense. Thank you.
Yeah.
Yeah, really nice work. Thank you.
Yeah, you can see that for this it's a set MAE. You can see that the raw is from 0 to 10,000. So they have it's pre-processing, I believe. Right. Right, the documentation is not that thorough, but in our code is actually we trying to make everything is follow the author's intent, follow the training strategies. So yeah.
Perhaps those are the types of questions that would be helpful in the documentation too. These are good questions to include. All right, any final questions? If not, I thank everyone very much. Thank you very much for the presentation today. This has been great. I know you've been working super hard on this semester. And thanks everyone for attending. As we said before, this is being recorded, and once the file's processed, it'll be up on the iGuide website. Stay tuned to that iGuide VCO webpage. We have lots and lots of good presentations coming up, almost weekly ones now through into the summer. So thanks again, and everyone enjoy the rest of your Wednesday. Take care.
Thank you.